Our next speaker is Adam Andersson. He works as a radar systems engineer at Saab Surveillance. He's a mathematician with a research background in numerical analysis and probability theory, and he will be talking about removing computational bottlenecks with deep learning. Welcome, Adam.
Thank you very much. So in this talk, I will speak about how to use deep learning to accelerate or enable white box models. And by white box models, I mean solvers of mathematically well-defined problems. Yes. And I will present two different projects that were done by master thesis students in the last one in the spring and one about 2-3 years ago. And the first one is about Bayesian statistics, is related to what Christian Forsén talked about. So I will give you a second review of Bayesian statistics, and the second one is about optimal control. Yes. Okay, so something about Bayesian statistics. So it's statistics, and in statistics we use data. We call the data Y. And we have some parametric family of models. We call them P of Y, given theta. Theta is the parameter. So our hypothesis is that for some parameters, this model will describe the data better than for other. And we want to find, say, the distribution of the parameters given the data. And in Bayesian statistics, you have a prior, so you have some initial guess about the parameters, and you're interested in the posterior distribution, which you see on the bottom left. And in practice, it's seldom explicitly attainable, but rather you need, or it's common to use some approximation methods like the Metropolis-Hastings algorithm, which defines a Markov chain. That's a sequence of random numbers whose stationary distribution has the same distribution as the posterior distribution. And I will show how to speed up this process. So to the left, we initialize the chain. So we sample theta 0 from the prior, and then recall that we want to sample from a difficult posterior distribution that we know little about. We can't sample it directly, so therefore we sample a so-called proposal from some well-known simple distribution, and then we generate a so-called acceptance probability that tells us with what probability we should the next the chain should make a transition to that proposal or stay constant. But in the computation of the acceptance probability, you use a so-called likelihood, which you see in the middle, and there the data comes into play. And that is the bottleneck that we will attack with deep learning. So we run the chain for a while and collect proposals and train a neural network, a small, simple one, and replace, once it has been trained, we replace the log likelihood computation with the neural network. And we also check that if the likelihood value is outside, or the proposal is outside, say the set that the training proposals spans, then we use the likelihood instead, so that we don't use the neural network unless we believe that it gives a good approximation. Okay, so here are two figures from the master thesis project. It's a very small toy problem, but it shows the principle. we start. I said that the Markov chain it approaches its stationary distribution is the posterior distribution. So in the beginning, if you start badly, it will not be close to that, and that you see to the left here. That it is so-called burn-in period, where you cannot use samples from the Markov chain in order to sample from the posterior distribution. But you see here that perhaps after 500 iterations, it has converged pretty fine, and then you can start to sample. But you see that it's constant during long periods because it doesn't accept all the proposals, and so therefore you cannot pick every sample, but you need to wait so that you get essentially independent samples from the Markov chain or from the posterior distribution. And to the right, we see the time it takes to generate a certain number of essentially independent samples from the posterior. So on the x-axis, you see the number of samples, and on the y-axis, you see the time it takes. Because of the burn-in period, it takes for this simple toy problem about 11 seconds to generate anything. And then just for a tiny short time, the method starts. We start computing posteriors or proposals, and after that we train a neural network that when the blue curve goes up, because it doesn't generate anything, it trains the neural network. But when it is trained, you see that it's so fast so that you hardly see the slope in the graph. And you see that if you want more than 150 points or sample more than 150 points, you should use this method. And the master thesis was done by Elias Hörlin-Hanusch and Oskar Holmstedt, and it was also supervised together with Umberto Piccini at Chalmers. And I think it explains quite nicely that you have an algorithm, and you keep as much structure as you can, and you remove just the bottleneck and get a very good performance and a good explainability also. Of course, you have a small black box, but it's most of the algorithm is still, you can tell someone what it actually does. Okay, so the second example concerns optimal control. And one of the examples is this double inverted pendulum that you see on the left. And it is supposed to be controlled in terms of in an optimal way, where optimality is defined by this cost function J that you see to the right. It has a term G that penalizes behavior at the terminal time, and it has the second sum which penalizes the behavior during the time until the final time. And X here is described as a state space model, or you could think about it as a discretized stochastic ordinary differential equation. And this problem, the previous problem was about acceleration, something that we could do something about before. We could do faster, but this is more of an impossible problem if you do it without some kind of approximations. Usually, you approximate the model. You take a simpler model. For instance, you linearize the pendulum around some equilibrium point, and then you have a regulator which works very well around this point. But if you push it, it will go outside this region, and you will have a regulator that will fail. But now we're trying to hit the fully nonlinear problem. And yeah, the approach is to take simply. So I will present two different algorithms. One which is doesn't use much of theory at all, perhaps a little, and the other one a bit more. And the first approach is to take a function which, in every time step, we have a small neural network which takes the state x and generates control u. So let's look at this. You see it on the graph to the left that, say, given x0, we have a neural network which generates u0, and given u0 and the noise increment, so that's delta w is normal Gaussian, we compute x1. And then given x1, we have another small neural network with the same architecture that generates u1. And given u1 and the noise and x1, we have x2, and so on. And you could think about this as a big neural network which takes x0, that's the initial value, and the noise increments as input, and outputs the state x and the control u. And if in our case we had 3 hidden layers in the small neural networks, and you can think about computing the x1 and x2 and so on as a deterministic layer without without parameters. And then if you say, for instance, you have 100 time steps, then you will have a neural network with 400 layers. But it's still quite small, and it works well on a laptop. Yes. And to the right bottom, you see the loss function. We simply use the cost function of the control problem and replace and use this mapping from x to the control and try to fit the theta in a good way. So I think this would be a natural approach for someone that doesn't know control theory, that doesn't, it's quite natural. I will also say that it was done, this method is from a paper from 2016 from the NIPS conference. So is it a good approach? Does theory support that the optimal control is actually a function of the state? Yes, it does. You see this theorem, which is a theorem with some more details. It says that the optimal control is a function of the state. So this ansatz with taking a function from state to control makes sense. But the control or the theorem also says something more. It says that that this g function has some more structure. It's a function h of state and the gradient of some function v of time and state, where h is of this certain form that we see here. For your application, you have to compute it. For many applications, it's explicit. And you don't need to solve an optimization problem. And V here solves an Hamilton-Jacobi-Bellman equation, which is for the doubly merged pendulum is a 6-dimensional PD, and there is no computer in the world that solves this equation when it's except in trivial cases. So it's a hard problem if you want to solve it exactly. So our second algorithm uses this function, this relation with a function h. So instead of generating the control u, it instead generates the gradient of v. Of course, the neural network doesn't know that it generates a gradient of any function, but it generates something of the correct dimension, and then the single arrow up to u0 and the u1 and so on is just this h function, which you can think about as an extra layer, and you give the network a little bit more structure than just using a black box, so to say. We also looked at algorithms that attacked the Hamilton-Jacobi-Bellman equation, but I will more about that soon. Yes, so these are some results. It's from a master thesis that I supervised 2018 by Christopher Andersson. He's now a PhD student at TU Delft, very competent. And you see to the left that this that algorithm 1, which is the green curve, performs really bad, and algorithm 2, which is the orange curve, performs much better. The blue one attacks the Hamilton-Jacobi-Bellman equation in terms of an equivalent formulation with the so-called forward-backward stochastic differential equation. But you see that it doesn't give anything extra. And it turns out also that this the algorithm 2 is also more stable in training, so it's easier and performs very well. But we also look at a simpler problem with a linear spring mass system, where we also have an exact control that's given by the black dotted line. And here, algorithm 1 trains best. All of that, it's such an easy problem that all of them learn what they should. But algorithm 1 learns faster. Yes, here's an example of this. Of the pendulum. And here's another. And the nice thing is that it works for many initial conditions. Yes, and the concluding remarks, I think using as much structure as possible increases transparency, modularity, and explainability. We don't use a black box for the whole problem. We try to isolate subproblems. And as you saw previously, for instance here, we had a neural network with where the input are normally distributed. So here x0 is uniformly distributed and delta w is normally distributed. So when we train our neural network, we just need to sample from very well-known and simple distributions, and we don't need to think about the data quality or such issues. Yes.
Thank you, Adam. So let's go to the questions that we have had so far. So is this approach of solving the optimal control theory, could you use that for any kind of stochastic differential equation? Or is the methodology restricted to exactly these kind of problems that boil down to the Hamiltonian Jacobi differential equation?
I think there is a connection between partial differential equation and stochastic partial differential equation. And if you want to solve a partial differential equation, say of second order, then you will, and also parabolic, then you have a good chance of, you can try this kind of relations. But some other times you might just want to simulate an SD and so on. And so it depends on what you want. Yeah.
So, and in the comparison with the classical way of solving that problem, right, in the graphs, is your method computationally more efficient? Or
yes, it's very efficient.
Okay.
Yeah.
So how much faster are we talking about?
I mean, you're talking about something. If you don't do a simplification of the problem, then you can't do it.
Right. But comparing to the other approximations that you...
if you use, for instance, if you linearize the problem around an equilibrium point, then that will be almost as fast.
Okay.
But you cannot continue to control if the state leaves this area where the regulator works.
Okay. One question more. Jesper is asking, could you expand a bit on if there is some relationship between the deep learning Bayesian inference paper and some model-based reinforcement learning?
I cannot answer that question because I haven't studied that, the model-based reinforcement learning.
Okay.
So,
I guess you will have to discuss that with Jesper at some later
Yes.
point.
yes.
Okay, thank you, and welcome Anna with the flowers.
Thank you.